Welcome everyone. So this is the sixth class of this chapter atom. So in this class we will going to discuss about the X-ray part. In previous classes we have covered almost most of the syllabus we have already covered. We have started from the Dalton hypothesis, then we covered Rutherford atomic model or planetary model, then in elaborate way totally we have discussed the Bohr atomic model, which is very important. We know, we have already understand that why it's so important, what is the applications of Bohr atomic model to explaining in hydrogen atom spectra, because hydrogen atomic spectra was very ridiculous in nature, as we discussed in the last classes. We have also discussed about the types of spectrum, absorption spectra, emission spectra, and the other classification like line spectra, continuous spectra, or the band spectra. These things we have already discussed, and also we have discussed how Bohr model just very easily Bohr's model can explain these results, these observations, but there are some also flaws, drawbacks and limitation in Bohr's model. There we have also discussed that, because there are some ad hoc assumption, as we know, in terms of Bohr's postulate, right? So these assumptions are there. So basically there, in case of the Bohr's quantum postulate, there are no basic concept why Bohr considered that MVR equal to NH by 2 pi. This was just kind of back calculation. I have already discussed these things, that Bohr just considered that MVR equal to NH by 2 pi so that he can explain the experimental observations. But nevertheless, Bohr's atomic model is very important, and it's a genius example of what I can say is great discovery. Okay, so now in this class I will discuss the X-ray part. It's also very important. So let me start. X-ray, we are very much familiar with this term, right? X-ray in daily life we are very aware of this term, right? X-ray in medical science, or we know in diagnosis for the bone fracture or these other medical cases, this X-ray is widely used. This is very common name. But as I discussed in the electromagnetic waves part, or in this part as well, if we see the total spectrum of light, there are very small range which is visible range that we can actually visualize through our naked eyes. So now if you classify this part, already we have discussed, right? This is, if this is the total range of light, electromagnetic wave, yes, electromagnetic waves, let me write it short. Okay, in case of wavelength, 400 nanometer to 700 nanometer. In case of wavelength in nanometer, this part basically is our visible region, right? This is our visible region. Okay, around 400 nanometer, those wavelengths looks like violet, and around 700 nanometers is just red. So in this region there are VIBGYOR. Okay, now if you classify from the beginning in terms of wavelength, as I mentioned, okay, one thing we have to again remember, that nu, the frequency, into wavelength is equal to the speed of the light. So nu lambda is equal to c. So it's clear that lambda proportional to 1 by nu, because in free space c is constant, which is 3 into 10 to the power 8 meter per second. Okay, this c is constant, so obviously in free space lambda and nu are linearly not proportional, lambda proportional to 1 by nu. Okay, inversely proportional. Okay, now so when the lambda is increasing, we can say that the nu is decreasing, the frequency is decreasing, and we know from Planck's hypothesis that if proportional to nu, that means c equal to h nu, so we can write it hc by lambda. This is also well known, these two equations. So here also, from here we can say that the energy of that photon of particular wavelength inversely proportional with that wavelength. That means if you increase the wavelength, the energy of that particular photon will decrease, that means the frequency will increase. So it's clear, if wavelength increases, that essentially means that frequency will decrease. That means the energy of that photon, energy of photon of that particular frequency will also be decreased. Okay, these things are very much clear, I think, because we have already discussed in the dual nature of matter and wave, that part, radiation, that in that chapter these things are already well covered. So I'm not going to discuss in details those things because these are now very much trivial for us. Now we have to consider that light, electromagnetic radiation, we know that there are dual nature. In case of matter there are some wave property, and in case of wave or radiation as well there are some materialistic property, that means particle nature, or we can say photon, particle of the electromagnetic wave is called photon. Okay, but when the X-ray was discovered, if we go according the timeline, so we can see that the X-ray was discovered in 1895, so we can say late 19th century. So in 1895 there was no concept of quantization, quantum mechanics, dual nature. This concept was not known because in 1905, as we know, the Einstein did the photoelectric effect, explained the photoelectric effect. In 1901 Planck give his equal to h nu, Planck's hypothesis, and after that also de Broglie came later, Heisenberg, these people came later, but this dual nature was not known. Dual nature known around 1920, in this time. So we can say that X-ray was invented before this concept. So this was now recent explanation after discovering the after understanding this dual nature part, we can understand. But before that, that light is a wave, light is a particle, though means it has dual nature. Photon is there, photon is the particle of light, so it has a particular wavelength or frequency, which is, we know that E proportional to nu or the inversely proportional to lambda. These things are not known. Okay, these things are not known at the time of discovery of the X-ray. Who discovered the X-ray? This is very important. Röntgen did experiment, and Röntgen discovered the X-ray. German physicist Wilhelm, not William, sorry. Röntgen, this is the spelling. He discovered the X-ray at 1895. How? Actually, he was doing the experiment with the cathode ray. What is the cathode ray? Cathode ray we know, right? Cathode ray is flow of electron. Electron was already discovered. Who discovered the electron? J.J. Thomson, right? J.J. Thomson discovered the electron, but cathode ray is just the flow of electron. Now, what Röntgen did, he was using the cathode ray. Let's say this is some cathode tube. Okay, cathode ray was, how cathode ray was generated? Just like, let's say there is some potential, yes. So we can say this is negatively charged, this is positively charged, so electron will flow in high velocity. So this looks like ray, because in that time, when cathode ray was discovered, it was not known that that is the flow of electron, but it was known that that is a flow of the negatively charged particle. Later it was identified as the electron by J.J. Thomson. Okay, these things we know. So this is the cathode ray, electron was moving in the cathode tube, and Thomson kept a solid here, this is some solid species in the trajectory. Okay, so what he obtained, that when this cathode ray collide with this metal, one ray is coming out from that metal, unknown ray. There was no concept about this ray in that time. So this ray was identified by Röntgen, and he termed this ray as X-ray because this was unknown ray. We know in mathematics we used unknown properties as X, right? We termed. So in similar note, Röntgen named it X-ray, that means the unknown ray. Okay, so in this way the X-ray was discovered. What was the properties of X-ray the Röntgen get? First property was, this ray, X-ray, can produce fluorescence. Okay, what is the fluorescence? Fluorescence, okay, we can discuss in short. Let's say there is some object. If from that, if you impose some light in that object, any light, then that body become brighter, and that body also can produce some light, we can say. So that is the fluorescence. We can think like, if let's say there is a wall, okay, and if you give light there, then that wall or that things will glow. That is the fluorescence. Okay, and that materials is called the fluorescent material. The property, the physical phenomena is called fluorescence, and that particular the particular element which is showing this nature, this fluorescence, is called the fluorescent material. Okay, so X-ray can produce fluorescence, means if you impose X-ray on that fluorescent materials, fluorescence can be obtained. So X-ray has had this property, also has. Okay, X-ray can affect photographic plate. Okay, so when the X-ray is emitting from that solid after hitting by the cathode rays, that ray can affect means can destroy the photographic plate. Okay, it will make a spot there. Okay, this is also the property of X-ray. Third property is it can penetrate. X-ray can penetrate thin sheets like paper, glass, wood. These things can be penetrated. Okay, that X-ray is emitting from that solid. If you kept a thin paper or glass or wood, then the X-ray will penetrate. Okay, and after that wood, if you put the photographic plate, that photographic plate will be affected, which proves that the X-ray actually penetrate that particular paper, glass or wood. Okay, so X-ray can penetrate, but X-ray can't penetrate the heavy metals. X-ray can penetrate the heavy metals. Okay, like iron, lead. Okay, these things cannot be penetrated. Okay, and the last, these natures, these properties of X-ray was not matches with any known rays. So that's why it was named as X-ray, as we discussed. And this X-ray, actually X-ray are not streams of charged particle. How it can be confirmed? It can be confirmed easily. If you put an electric field there, then it will not deflected in the, let's say the X-ray is emitted. So in the path of X-ray, if you put an electric field plus minus, it will not deflected. If it is a flow of the negatively charged particle, obviously it will attracted towards positive side. If it is the flow of the negatively charged particle, positively charged particle, then it will be deflected towards the negative part. But actually it is not deflected to any direction, it goes straight. So it means that it's a flow of, it's not the streams of the charged particle. It is confirmed. So then what it can be? What is the X-ray? So this observation actually proves that, confirms that X-ray is either a stream of or flow of high velocity uncharged particle. It should be. Why high velocity? Because that's why it looks like a ray. Cathode ray is not a actually ray. We know ray means wave, we know, but cathode ray is a flow of electron. Electron is a negatively charged species, but it moves with a high velocity. That's why it looks like a ray. So it's possible in case of X-ray also that it's a flow of high velocity uncharged particle, right? Or what it can be? It can be any kind of wave like sound or light. Ironically, X-ray is both, because now we know the dual nature, right? X-ray is actually light, electromagnetic radiation, it's a wave, electromagnetic wave, it's correct, but also it's a flow of uncharged particle, that is photon. Okay, so both is correct, it's not either or, it's actually both. This is the dual nature. Now we know these things, but in that time that was dual nature concept was not there. So they thought either X-ray may be a wave or it may be a flow of high velocity, flow of uncharged particle which is moving in a high velocity. So this was the observation, and after seeing the experimental result, the scientists make this conclusion regarding the X-ray. Okay, so later it was proved that X-ray is actually flow of X-ray is actually electromagnetic waves. That was later understand. Okay, it has been observed that because in that time there was no concept of photon, so we have to keep in mind that we are in the late 90s. So in that time there was no concept of photon, so we have to delete that we know about this photon, this dual nature, we have to delete that. Okay, so at that time, after discovery of X-ray, after doing several types of experiments, it was observed that X-ray is not a stream of any high velocity uncharged particle, but it's actually an electromagnetic wave like our visible light. Okay, why this observation was obtained? Because now we know there is photon, but actually photon is massless particle, right? So when the experiment was done, the measures how electron was identified. Cathode ray was flowing. Now Thomson did the experiment and he obtained a mass, that is the Me, and the charge, Q by Me ratio, right? We have discussed these things. Q by Me ratio was obtained. But in case of photon, in case of X-ray, we can say Me is 0, right? There is no mass. If we consider the photon also, there is no mass. So that's why there was no result. The observation, that's why proved that this is a flow of a electromagnetic wave. This is not a flow of particle. If there is a particle, then that particle should have any mass, because in that time there was no concept like photon. Okay, so obviously like electron is a particle, electron has a mass, though it's very less, but it has a mass. It should be identified in experimental setup, but in case of X-ray, that was not the case. So X-ray was in experimental, it was found that it does not have any mass. So which essentially means that it should be a wave, because particles should have the mass, right? So that's why the experiment suggests that it's a electromagnetic wave like our visible light. It's not a flow of the uncharged particle. So now how this experiment actually was done, that we have to first understand, then we will go into that part details. Okay, so now let me write it. If X-ray was considered as a wave, considered to be kind of wave, it should be, we know that wave shows variety types of properties like interference. Okay, most important property, interference, reflection, diffraction, these properties was shown by the waves, right? But in case of X-ray, it was not evident actually. X-ray was not showing these properties. So it was a very difficult situation. Then what is the X-ray? So in that time, we can say the Max von Laue, he did some experiment and he observed the diffraction. He observed the diffraction of X-ray through the three-dimensional crystals, means solid. Okay, so it proves that this experimental result proves that X-ray was a wave. This is also one kind of experiment. There are several types of experiment which proves that X-ray is a wave. Okay, so diffraction means we know it deflected when it passed through some object or body. It deflected. It's a property of wave. Let's say interference also, it's a property of wave. These things already we know from our wave mechanics. So, but in case of X-ray, to obtain that diffraction, we have to use the three-dimensional crystal. When in case X-ray passes through this three-dimensional crystal, any solid, crystalline solid, then X-ray deflected, we can say. So this deflection was obtained. This experiment was done by Max von Leu. So it's a very important experimental result. Okay, so then what was the outcome? So outcome was the wavelength of this ray, that means the X-ray, is so small that its diffraction is possible only by crystals having the space 10 to the power 8 centimeter. Okay, so means that in case of crystalline solid, the space between the atoms, you can say, is very less, 10 to the power 8 centimeter minus 8 centimeters. So then only that space is equivalent to the wavelength of X-ray, which makes the diffraction. So it is proved that the wavelength of X-ray is very small. That's why we have to use very small, we have to use a crystal, three-dimensional solid crystal having very small parameters, 10 to the power 8 centimeter, so that it can make the diffraction. So this was the observation. So from here we can say that X-ray, wavelength of X-ray is very small. But this, after this experiment later, there are several kind of experiment by which it was proved that the X-ray goes through the refraction, reflection, interference, polarization, this also. So X-ray also shows interference, reflection, refraction, these things, like just like our visible light. So from here it was proved that X-ray is just like it's an electromagnetic wave, just like our visible light. Okay, so now we know that in vacuum all electromagnetic waves runs in a constant velocity, which is 3 into 10 to the power 8 meter per second. This was also known. So this was observation, this was the result obtained during the experiment with the X-ray. So it was proved that X-ray is a electromagnetic wave, not a flow of the uncharged particles. Okay, so this is great. And also it was also evident that X-ray has a very small wavelength. Okay, so thank you for paying attention with me. So let's meet again in the next class. Thank you.